You know that feeling, right? You open your email and it's just clean. All the junk mail, all the scams have just vanished. It feels like magic. Well, I'm here to tell you it's not magic. Today, we're going to pull back the curtain on the surprisingly simple and kind of brilliantly naive algorithm that makes it all possible. I mean, really, how does it know? How does your inbox know that an email about a long-lost fortune is total junk, but a message from your friend about their new puppy is the most important thing in the world? It's a great question. And the secret has nothing to do with magic. It's all about teaching a machine how to sort our digital lives. So to really get this, let's just imagine a tiny little robot living inside your computer. This robot is our algorithm. And think of it as your own personal digital mail carrier with maybe the toughest mail route on the entire planet, your inbox. Every single day, this little robot is just hit with a tidal wave of messages. We're talking hundreds, maybe thousands of them. And for every single one, it has one job, and it has to do it in a fraction of a second. Make a decision. Is this important mail, what we'll call ham, or is it junk mail, what we call spam? Now, obviously, our robot doesn't just know how to do this right out of the box. It has to be taught. And this whole process, this idea of teaching a computer how to sort things into different piles, well, that's a cornerstone of machine learning. It's a process called classification. And at its heart, the idea is really simple. You're just feeding the computer a piece of data, like an email, and teaching it to slap the correct label on it. You're teaching it to put things into the right buckets or, the right classes. In our case, the input is the email itself, the whole shebang, the text, the sender, all of it. And the output is just one of two very simple labels, spam or ham. And this concept of classification, it is everywhere. It's the same core idea that allows a machine to look at a fuzzy, handwritten squiggle and correctly label it as a 7 or a 1. It really doesn't matter if you're sorting numbers or emails. The principle is exactly the same. Input, analysis, and then an output label. So how does our robot find the clues to make its decision? Well, it looks for things we call features. These are just the attributes of the email that it can analyze. Some are really obvious, right? Specific words like free or money, but it can also be more subtle, like text patterns. Is the subject line all caps? Or it could even be who sent the email. Are they in your contact list? All of those are clues. They're all features. Okay, now for the really cool part. To process millions and millions of emails, our little robot needs a shortcut, a secret that makes it incredibly fast and efficient. And the secret is, well, it's a little bit naive. I mean, think about it for a second. An email could have hundreds of words. Checking how every single word relates to every other word would be, well, it would be computationally impossible to do that for millions of emails every day. So, what's the shortcut? The algorithm behind our robot is called naive Bayes, and it makes one big, bold, and frankly completely wrong assumption. But it's this exact assumption that makes it so powerful. Here it is, the naive assumption. The algorithm assumes that every single feature, so every word in that email, is completely independent of all the others. It basically just pretends there's no relationship between them at all. Now, in reality, we know that's not true, right? In spam emails, the words prince and money are very much related, but the naive Bayes robot just pretends they aren't. It sees the word prince and treats it as one clue. It sees the word money and treats it as a totally separate, unrelated clue. This is exactly why it's called naive, and it's also what makes the math so simple and so incredibly fast. So, with this simplifying assumption in place, how does the robot actually learn what spam even looks like? Well, it does what any good student does. It studies thousands and thousands of examples. The source material we're looking at gives a fantastic analogy for this. Imagine I hand you a thumbtack and I ask you, if I flip this, what's the probability it will fall with the nail pointing up? You can't just know by looking at it, right? You'd have to gather some data. You'd have to run an experiment. You'd flip it and flip it again. And again, you would just collect evidence, one observation at a time. Up, down, up, down. So after just 5 flips, our best guess is that the probability of it landing up is 3 out of 5. The spam filter learns in the exact same way. It analyzes thousands of emails that have already been labeled by humans, and it just counts. It calculates the probability that the word free shows up in a spam email versus a ham email. It builds its knowledge just one example at a time. Okay, but here's a tricky problem. What if our robot, after all its training, gets a brand new email with a word it has never, ever seen before? A word like blorg. Well, if that word never appeared in its training data, the robot would calculate its probability of being in a spam email as 0. And because the naive Bayes formula multiplies all the word probabilities together, multiplying by 0 would make the entire spam score for that email 0. This one new word could break the whole system. The fix for this is a really elegant trick called Laplace smoothing. It's simple. You just pretend that every possible word has appeared at least one more time than it actually has in your data. This small adjustment adds a tiny little bit of probability to every word, and it makes sure that no single new word can ever have a probability of 0 and crash the whole system. So you might be thinking this whole naive assumption sounds like a huge flaw, but as we're about to see in practice, its simplicity is actually its greatest strength. So here's the genius of it. Because it treats every word independently, it is incredibly fast. It also doesn't need nearly as much training data as more complex models to start getting good results. And for tasks like sorting text, spam filtering, sentiment analysis, you name it, it works shockingly well. It is a true workhorse of machine learning. So what it really comes down to is a trade-off. Naive Bayes gives up on trying to understand the perfect, complex relationships between all the words in a language. But in return, it gets blazing speed and remarkable efficiency. And for sorting your email every single day, that trade-off is almost always worth it. Which leaves us with a final thought. In a world that is constantly chasing bigger, more powerful, and more complex AI, it really makes you wonder, when is the simple, fast, and good enough solution actually the most intelligent one? When is being a little bit naive actually a superpower?